Hello, my name is Emily Lazarus, and this summer I worked in the interdisciplinary manufacturing, engineering, and design lab under the advisement of Dr. Iris Rivero. Today I will be presenting my research project, which focused on the influence of 3D printed scaffold geometry for trabecular bone regeneration. High-energy fracture injuries and bone disease, like osteoporosis, which affects more than 200 million people worldwide, are some conditions that result in bone loss. Unlike softer tissues such as cartilage, bone tissue is capable of regeneration and does not differ structurally or mechanically from the surrounding undamaged bone tissue. Despite this, depending on the extensiveness of bone loss, regenerative properties of the native tissue may not be enough for proper healing. 5 to 10% of fractures are prone to non-union healing. Autografts and allografts are commonly used to treat bone defects, but limitations of donor site morbidity, infection, and pathogenic immune response have necessitated the development of new medical and clinical strategies. To overcome these limitations, alternative tissue engineering methods have been developed to combine scaffolds, cells, and cellular signals into a functional tissue construct. Three-dimensional printing has emerged as a versatile technique for scaffold fabrication with controlled pore size, geometry, and porosity. These properties provide a biorelevant architecture for proper cell proliferation and differentiation for the treatment of bone defects. Pore geometry is a key structural parameter affecting mechanical strength and biological activity of bone cells on 3D printed scaffolds. Cellular interactions are dependent on scaffold shape, and these interactions determine cell infiltration and spreading, and therefore differentiation. The use of 3D printing isolates pore geometry for the above to be studied. To investigate the effect of scaffold pore geometry on bone regenerative scaffolds with properties suitable for trabecular defects, the object of this work is as follows. First, we validate the fabrication and characterization of PCL HAP powders using cryogenic milling and confirmed printing parameters that yield high-fidelity three-dimensional shapes with specific pore geometries. Additionally, the characterization of 3D printed scaffolds was assessed. Polycaprolactone, or PCL, is commonly used for bone regeneration due to its biocompatibility, degradation rate, and melting properties, which make it ideal for extrusion-based printing. However, PCL is not osteoinductive. Therefore, mixing this polymer with a bioactive ceramic, such as hydroxyapatite, or HAP, creates a bioactive composite with enhanced biocompatibility, mechanical strength, and hydrophilicity. Additionally, HAP promotes proliferation and differentiation of osteoblasts. Cryogenic milling, a technique that subjects the material to repeated fracturing at cryogenic temperatures through collisions of a high-energy impactor, was utilized to create powdered composites containing varying ratios of PCL to HAP. To validate the fabrication process of cryomilled powders, scanning electron microscopy, or SEM, and electron dispersion spectroscopy, or EDS, were performed to ensure a homogeneous blend of PCL and HAP. To validate printing parameters, parametric optimization for each powder composition was carried out in 2 steps. In the first step, Printed strands were photographed and measured using image J to identify parametric combinations of printing pressure, speed, and temperature that yielded strand widths between 360 to 440 microns. In the second step, the identified combinations were further shortlisted by measuring strand areas of 3 different printed contours, square, triangle, and hexagon, and comparing them against their theoretical counterparts. At the end of the second step, we identified a unique parametric combination for each composition theoretically capable of yielding high-fidelity 3D scaffolds. To study the influence of pore geometry, scaffolds with 4 different pore geometries, grid, overlap grid, triangle, and overlap triangle, were designed to have pore sizes between 350 to 500 microns. The scaffolds were 3D printed using the optimum parametric combinations identified from the 2-step optimization tests. The characterization of the 3D printed scaffolds was carried out through the analysis of scaffold surface roughness, contact angle, accelerated hydrolytic degradation, and compressive strength, which are scaffold properties crucial for proper bone treatment. These tests were performed for all scaffold material compositions in all pore geometries. SEM imaging of the composite powders shows the powders were composed of rounded particles that expressed a decrease in size from the non-cryomilled PCL control. EDS element mapping of the powder materials confirms homogeneous dispersion of calcium and phosphorus throughout the cryomilled powder composite. These results validate that cryomilling is an appropriate technique for fabricating PCL and HAP powders. Cryomilling allows for decreased milling time as compared to other methods such as solvent casting, because the processing temperature is much lower than the glass transition temperature of PCL, which facilitates the occurrence of brittle fractures. Additionally, cryomilling ensures a homogeneous blend of dissimilar materials. Initial strand tests revealed that a decreasing average strand diameter was evident with an increasing linear print speed. This trend is related to the material extrusion rate when a defined pressure and temperature are applied. Strands with a larger diameter than the print nozzle experience a greater extrusion rate as compared to the linear print speed, resulting in excess material deposition. The arithmetic average of the absolute roughness and the root mean square roughness were measured for each material composition. Overall, an increase in HAP content showed an increase in surface roughness, which is due to HAP creating increasing local deformities in the material. An increase in HAP content caused a decrease in average contact angle. This is due to an increased scaffold hydrophilicity with the addition of HAP. Hydrophilicity is an important factor for increased cell proliferation. Scaffolds were submerged in 5 molar NaOH for 4 days. The strand size of the scaffolds was observed to decrease in size over time until the scaffold was completely dissolved. An increase in HAP content caused an increase in degradation rate. It is important for the scaffolds to degrade at a rate which mimics the regeneration of bone, which is around 5 to 6 months. Pure PCL degrades slowly due to its hydrophobic properties, so mixing the polymer with a ceramic like HAP improves scaffold degradation to mimic the regeneration of bone tissue. 3 samples of each printing geometry and material were tested, and the mean compressive stress were determined. Through the comparison of printing geometry on compressive modulus, the grid geometry had an overall higher compressive modulus for each material than the overlap geometry, which was also true for triangle geometry as compared to overlap triangle. This trend is due to the strand orientation of the grid and triangle scaffolds as compared to the overlap counterparts. Grid and triangle geometries experience strand penetration between each deposited layer. Additionally, an increase in HAP content expressed an increase in compressive strength. All results were comparable to reported results of trabecular bone. In conclusion, cryomilling achieved a homogeneous powdered mixture of the polymer PCl and ceramic HAP without any alterations of material properties. The characterization of PCl HAP 3D printed scaffolds showed mechanical properties similar to trabecular bone and degradation rates needed for bone tissue regeneration. The pore geometry of the 3D printed scaffolds did influence scaffold properties, such as compressive strength. In the future, cell studies should be conducted to study the influence of geometry on cell proliferation and differentiation.